Okay, welcome back, Year 12 Single Mathematicians. So we're just going to continue with 10.6 again, which was on pulleys, but it's a different style question. There's going to be a table involved for this one. So you've got, again, a very wordy question, but two particles, A and B, of masses 0.4 kilograms and 0.8 kilograms respectively, are connected by a light inextensible string. Particle A lies on a rough horizontal surface, in other words, table, so something like this. And that's 4.5 meters from a small smooth pulley. So there's the pulley at the end, and that distance there is 4.5 meters. The string passes over the pulley and B hangs freely with the string taut. So there's a string there, hangs over the edge, and B, it's not in contact there by the way, just hangs freely with the string taut 0.5 meters above the horizontal ground. So not to scale, definitely. 0.5 meters above the ground. A frictional force of magnitude 0.08 G, yeah, because this was a rough surface, opposes the motion of A. Should be newtons. The system is released from rest. Find the following. Acceleration of the system. Now, which way is the system going to move? It should be pretty obvious that it's going to try and go down this way. So B is going to try and go down, so the acceleration will be in that direction, which means A is going to go to the right, acceleration in that direction. And same strategy as all of these. The first thing we do is resolve one of the particles. So let's resolve particle A. Force is acting on particle A. Has a weight. Its mass was 0.4, so 0.4 G newtons. It's in contact with the surface. Reaction force, call it RA, newtons. Done the friction, is already in. It's attached to a string, so there's going to be a tension, T newtons. And that's it. That's the forces acting on object A. So I'm going to resolve horizontally. In this horizontal direction, it is accelerating. So F equals ma. The mass of the object is 0.4. The acceleration of the object is A. And now we have to work out the resultant force. Force is going with the motion, subtract the forces going against it. T subtract 0.08 G, and you've got one equation with two unknowns. Alright, let's do exactly the same for B. Okay, force is acting on B, has a weight, 0.8 G newtons. Attached to a string, so there's a tension, T newtons. And that's it. And it's accelerating, so F equals ma. Mass of this object is 0.8. Acceleration is A. And the other way to work out the resultant force is forces going with the motion, subtract the forces going against it. 0.8 G subtract T. That's equation 1. That's equation 2. Two equations, two unknowns. There's a plus T, there's a minus T. So the best way to solve this is add them. Add them together. You have T's disappear. 0.8 G plus minus 0.08 G. I'm going to do this on a calculator. 0.8 minus 0.08 is 0.72 G. And that's equal to 0.8A plus 0.4A, which is 1.2A. Remember, G is equal to 9.8, so 0.72 times 9.8 divided by 1.2 gives you an acceleration of 5.88 meters per second squared. Okay. Part B. The time taken for B to reach the ground. So part B. B was 0.5 meters away. Time isn't like a forces question, so the only thing you can do is use SUVAT. So S, U, V, A, and T. It's got to move 0.5 meters. Initial velocity. Now let's check the wording. The system is released from rest. So initially it was 0. V is unknown. A is what we've just worked it out to be, 5.88. And T is given in the question, so, no, thing we want to work out, sorry. S, U, A, and T, we get S equals UT plus a half AT squared. Substitute everything you know in. 0.5 equals 0t plus a half 5.88 t squareds. And if you solve that equation by taking 0.5, divide by a half times 5.88, and square root, you get 0.412 to 3 SF. So that's the time taken for it to hit the ground. Now, part C changes everything. Part C is the total distance travelled by A before it comes to rest. And let's think what's just happened. B has dropped 0.5, which means A has travelled 0.5. Now when B hits the ground, the question changes completely because the string then becomes slack. There's no string at all effectively, and therefore this acceleration, it changes. It's no longer accelerating, that the actual object will start to decelerate. So, gonna need some more paper for this. So I'll just draw a new diagram out. So we have effectively the table, object A. Now, if you think about it, it was 4.5 meters away at the start, then it got 0.5 meters closer, so now it's 4 meters away. But this time there's no string, there's nothing attached to it effectively because it becomes slack. I'm going to pretend to do the question again. I'm going to find its acceleration. It's going to still try and move this way, but it's going to slow down. Force is acted on A. It's got mass, so it'll have a weight. It's got a reaction force, RA. and it's got friction resisting it because it's a rough surface, 0.08 G newtons, but no tension. Okay, it is accelerating because it's slowing down. F equals ma. Mass is 0.4, A is unknown. The resultant force now is the forces going with, which is 0. Subtract the forces going against, which is 0.08 G. And if you make A the subject, minus 0.08 times 9.8 divided by 0.4. It's a deceleration of 1.96 meters per second squared. Okay. Let's see if we can do that. So S, U, V, A, and T. S is the thing we want to work out, by the way. It was, if you remember, total distance travelled by A before it comes to rest. Initial velocity, I don't know. Final velocity when it wants it to come to rest, so 0. Acceleration is negative 1.96. And the time it takes to do that is, I have no idea. So I haven't got enough information. I've only got 2 things to work out a third, but I need 3 things to work out a fourth. So the last thing you've got to do is there is a way to work out its initial velocity. And the way to do it is go back to the previous workings, and if you think about it, B, the velocity that B is about to hit the ground with would match up with the velocity of A at the top, because the string would be perfectly taut. The velocity it's about to hit the ground with after it falls 0.5 will be exactly the same as the velocity of A at the top. So, some workings. I want this equation there, but I want to work out V instead. So that would be V squared equals U squared plus 2AS. 0 squared plus 2 5.88 times 0.5. And if you make V the subject, 2 times 5.88 times 0.5, all square rooted, gives you 2.42 meters per second to 3SF. So let me explain that again. So B hits the ground with a velocity of 2.42. which means A at the top has to have a velocity at 2.42 meters per second as well, which means when the string becomes slack, as in this example, it's moving with a velocity of 2.42, same as before. And now we've got 3 bits of information and a fourth unknown, and we have B squared equals U squared plus 2AS, 0 squared equals 2.42, use the exact version, 6S, add that to this side, that would be 3.92S equals this squared, which was that. And S would be 5.88 divided by 3.92, which is 1.5 meters. So it actually moved an extra 1.5 meters. But we wanted, back to the question, the total distance travelled by A before it comes to rest. So it travelled 0.5 meters when this fell, and then by itself it travelled 1.5 meters. So total distance equals 0.5 plus 1.5, which is 2 meters. And that's it. Okay, a couple of questions for you to try. Page 176 and 177. It's that same exercise again, 10F. And you're going to try question 4 and question 5. And then the good news is you're going to have a test on this chapter. So I'm going to send you a test on this chapter as well. Any questions at all, put a message on Teams and I'll try and respond as soon as I can.